Hi, today I would like to demonstrate a simple BWT algorithm with the approach of move to front, so that we can actually compress the data size. BWT is actually a very simple algorithm for data compression, and today we mainly focus on the move to front approach. So I just simply describe what the BWT is, and then I'll lead you through it. First of all, I'll give you a very small example. For example, there's like a pattern, there's like a sequence here. This is dollar sign. This dollar sign is $the. So our job is to try to compress this pattern, this sequence, try to encode it. So the first step we need to do is to just make a cyclic permutations. That means like a simple rotation. For example, I start with the second letter here, H, right? So H, IS, all the way to here will be the end of the sequence. And I simply just put the T, rotate the T to the very end. So for every rows here, I did the same thing. So I will be rotated to the next row, and then S will be the end of the fourth row, and then dollar sign will be the end of the fifth row, something like that, all the way to the end. And this would be the original sequence here. So as you can see, we do all the rotation, and then we got several columns. And what we need to concern about is the last column and the first column. So why do we concern about that? Let's see here. Originally, all these columns are not sorted. So I simply just, based on the first column I have here, I sort it with the lexical order. That means dollar sign is always smaller than, all those characters in the ASCII table, so you can look it up online. And then E is smaller than H is smaller than I is smaller than S is smaller than T. So we simply just sort them in a lexical order, and at the same time we actually sort this as well. So after we sort this whole table based on the first column, we got the last column, and this last column will be our BWT sequence. L means last column, so this string, this whole string, is going to be our BWT encoding. So what exactly this first column and last column is? So after we encode this, we try to decode this last column back to the original string. I'm not gonna describe all the detail here, because this is not the main point of this video. I'll just try to simply describe what exactly works. If you really want to understand what BWT is, there are tons of videos on YouTube, and there are a lot of materials online as well. So imagine that we only got our last column here. This is the only thing given. There's no first column, but we can simply just derive this first column based on the last column, right? So the first step is obtaining the permutation that is generate the sequence F, consisting of the first element of each row. So it's very simple to do, because we just simply sort this column based on the lexical order, and we get this column. So after we get this column, remember that I actually start the rotation from the second letter. So simply this column T here will be the first letter of my original sequence, because that's the rule that I make. So I basically just implement a forward search instead of a backward search. Backward search is like more traditional way to do it. Like you actually know the last character here, and then backward search backward and backward all the way to the beginning. But now I want to use a different approach to demonstrate. So I purposely use the first character here. The first character will be T, and we simply just sort this column and then get the first column, and then we get the very last index here, T. So when we find T here, T will be the second T in the first column. So we simply just go to the second T of the last column here, and then we, from this T, we refer to the same index in the first column. So the next character will be H, and this H will be the second H in the first column. So I refer to the second H to the last column here, and then I refer to the same index to I. So basically you can see that I is the first I in the first column, so I refer to the first I to the last column, refer back to the index, the same index, so it will be S. So as you can see, we got T, H, I, S. When we look back to the original string here, T, H, I, S. So basically all the way until we reach back to the first character T here. So that's called forward search. Well, the main point of today is to actually demonstrate how exactly can we further compress the BWT coding, so that when we face some situation like a lot of A in the middle, so we don't actually need to write all the A, but instead we can just use the bit to save more space. So imagine that we eventually got the BWT already here. So we simply just pick all the letters in a lexical order and then save it to another array. So this is like more like a dictionary. So a dictionary to refer to. Like, it's not actually a dictionary, but it's like a dictionary to refer to. So that actually contains all the letters we got, and then we simply just make a table from 0 to whatever number of the elements here. So from 0 to 5, because I have 6 elements here, so we start from 0 until 5, and then for each element we just refer, like, we correspond to like one number. The first step is to look at the first character of the sequence, the BWT encoding sequence. As we can see that the S is an index of 4, so we simply just record this index here. And then after this step, we move the S to the front, and then it becomes 0 index. So pretty much just move to the front and then shift everything in place. And we look at the next character here. Oh, it's S again. So that's a good thing, because we already went through S. The S is currently at the index of 0, so we simply just put the 0 here. And then after that, we'll look at the next character, The next character is H, so we simply just look up the table here and then find the index of H is 3. So I just simply put the 3 here and then move this H to the front, become the index of 0. And I keep the rest of the elements in order. The next character will be T. So I simply just look up T here, move to the front, record 5. The next character is T again. So because the T already at the index of 0, so I just simply put 0 here. The next character is H, and I record this index as 1, move to the front. The next character is $. I record the index here and then move to the front. The next character is I record 5 here, move to the front. Since the I is already at the index of 0, so I simply just record 0 here. The next character is $. Again. As we can see that there are 2 $signs here, but it's not consecutive. So we need to just put the 1 here and then move to the front again. And then the next character is E, so we simply just record 5. Eventually we got the encode with the move to front approach. So as we wanted that, the results are not too impressive with this small sequence, because we can see how, we can see how we could get large numbers of zeros, right, and small values if the sequence to be encoded was longer. Like for example, there's like a big consecutive of A or B in the middle. So those long sequences of zeros could then be efficiently encoded using schemes specifically designed for encoding long repetitions of the same symbol, such as run length coding. So this is our tutorial today. Thank you for watching.